invitation and the opportunity to present the project. So my name is Filippo Cugini. I'm from CNIT. CNIT is a private research company located in Italy. We have several labs. I come from the one in Pisa. The focus in our lab is on optical networks and technologies related to optical networks. In this project, I am the coordinator, but we have three partners, relevant partners involved. The other two partners are Telefónica from Spain and UPC, Universitat Politècnica de Catalunya in Barcelona. The project name is Reaction and basically deals with the flexible optical networks. So we tried to address all the topic listed within the call. So we'll briefly introduce the project, and then I will provide some background and some specific activities and outcomes. Then, as anticipated, if you are interested, I can provide also some information on the other project, the coffee project, which is handled by another CNIT participant and is a friend and colleague of mine. Okay, so as anticipated, this is the consortium. And so we will focus on flexible optical networks, and in particular the target will be the software control on high rate transmission. So also going back to the points addressed there, we are not really considering a multi-layer approach, so where we mainly focus on optical transport network. And in particular, we will consider the new generation of transponders, the so-called bandwidth variable transponders, that will enable a transmission beyond 1 giga and up to 1 tera. And the focus in particular will be on how to control the capabilities provided by these transponders, in particular in terms of adaptation. So we will focus on the adaptation of bit rate, baud rate, modulation formats, spectrum allocation, thanks to the flex grid capability, and specific focus on coding and FEC techniques. And in addition, we will consider also some capabilities called sliceability that I will show later with a slide. We will consider some, say, typical use cases, so provisioning, some elastic operations, so to increase and reduce the capacity allocated to a data connection, defragmentation and restoration, so traditional, say, scenarios. There are specific activities on algorithm in order to support all these use cases, and these algorithms will be incorporated in an architecture. The architecture will be mainly based on the GMPLS solution. So SDN will be slightly considered just as a reference scenario from some specific case, but this is a more, say, traditional approach based on GMPLS. So this also addresses one of the other gaps that might be covered by other activities. In particular, we will consider the most recent evolution of the path computation element architecture, which consider the active stateful functionality. I don't know if you are familiar, but I can provide some details on that. Also dealing with a very recent proposal called BGPLS to provide information to the path computation element. So SDN solution, as anticipated, will be considered, but just as for some comparisons. So we will target the scientific and technical objectives of the flexible optical network call. And the idea is also to specifically consider the NRAN scenarios. So I'm here also to kindly ask you to provide me information on your network, your ideal solution for transport in the context of transport network, also expectations in terms of traffic growth, dynamicity of traffic, granularity of traffic. So all this information could help us to provide to NRANs more, say, realistic information and more fruitful, say, information. And so in this information will be used to assess the possible advantage in terms of spectrum efficiency, CAPEX, OPEX, and all the typical cases that will be the outcome of the project. The project will include some activities run at through simulations, but also some experiments, mainly at the control plane level. In terms of simulation, we will rely on an OpNet modeler, and the code will be provided as an outcome. So, for if you are interested, we can, the code will be provided. Okay, this is an example of bandwidth variable transponder, and here the 1 terabit transmission is achieved thanks to the use of multiple carrier transmission. So given a certain baud rate, if we want to increase the capacity, we need to activate multiple carriers. And here in order to be flexible, we need to, for example, focus on different optical reaches that could be covered by different, for example, modulation formats. The adaptation from one modulation format to another is very easy from a transmission point of view. We can just switch on and off some tributaries and everything works. It's very easy. But it's not so easy if we consider the entire node, because we had to deal with the traffic that needs to be moved inside the node. Here is an example of a photonic integrated circuit that is able to generate either 16 QAM or QPSK. In the case we have a QPSK transmission, we just need 4 tributaries, because the 4 level with a polarization beam combiner here enable the QPSK transmission. If instead we provide to this element 8 tributaries, we have a 16 QAM transmission. So it's very easy to adapt from 16 QAM to QPSK, because we can just remove 4 out of 8 of these inputs. So from a transmission point of view, it's very easy. However, what if, for example, we have a shorter optical path, we configure 16 QAM, then there is a failure, we need to move, for example, the traffic toward a different route, and this route is longer. We need to move to QPSK transmission, which is more robust. But before, with 16 QAM, we had 8 tributaries. When we move to a QPSK, we just have to consider 4 tributaries. So what to do with the other 4? So we need an extra module here, an extra PIC. We need some flexibility here in order to move the traffic. Otherwise, we have to accept that half of the traffic will be lost. So this goes back also to the NRAN requirements. Do you accept that in case of failure, half of the traffic is lost? Or do we need to pay more in the node in order to introduce some flexibility here? And this node could be done at the electronic level or optical level with different performance in terms of recovery time. So we have different performance. So here is a matter of, so everything can be done, but it has a certain cost. So this is, for example, another, say, point of discussion. So these aspects will be considered in the project, so with a specific focus on the architecture that can provide the adaptation, because adaptation doesn't really come for free in terms, for example, of modulation format. Another aspect that was quite relevant for Telephonic as an operator, so might be relevant as well for NRANs, is the so-called sliceability. When we have a node like the one before, capable of generating multiple carriers, in this case, for example, 4. The idea here is if we have some flexibility in the node and we can route each of these carrier toward different direction, we could also think about having the first year to buy just one of these transponder in a node and send the traffic toward different destination with just one transponder. Then the following year we can add one additional transponder, that node, and we can reconfigure the route and also the way the single peaks are used in order to send the traffic toward different, in this case, 2 different destinations for the same 2 carriers. And maybe at the third year, the entire super channel will be dedicated to just one single destination. And this enables the operator, the NRAN, to buy at the first year one transponder, the second year maybe some other transponders, at the third year some other transponder, and not directly start with a configuration like this one. So, however, as you can see, there is a drawback in terms of spectrum utilization, because if you consider this solution, the carriers can be packed together, so there is a very high spectral efficiency. While if we keep them separated, we need to have more spectrum resources allocated to the transmission. So there is a trade-off here, and also we need to be capable inside the node architecture to configure the spacing of the carriers in a different way, in a configurable way. So this sliceable functionality can provide some advantage in terms of cost, but also in terms of, for example, survivability. So suppose that we already are in this condition, so the entire super channel is dedicated to a point-to-point communication. There is a failure. We are not able to recover the entire super channel because this amount of spectrum is not available on a certain path, alternative path. So we can also here in this case exploit this sliceable functionality in order to route each subcarrier independently. But as well, we need more spectrum resources, but in this case along different paths. So all these aspects will be addressed during the project in order to understand if they are beneficial or not, if they just provide additional cost and so basically this is the kind of activities that will be considered in the within the project. Another activity which relates to the architecture is also some functionalities like for example, the defragmentation. When we have a flex grid network with different modulation formats, different codings, different solutions, the granularity of the grid is smaller. We may end up with a situation which in principle should be more efficient, but maybe the network is fragmented. And so in this case, we can rely on some defragmentation solution, so re-optimization. And these new transponders enable some nice functionality. And this nice functionality is that, for example, a certain transmission, a certain channel, can be shifted in the spectrum hitlessly, so without traffic degradation. So this can be done while traffic is flowing in the network. And so we can re-optimize the network if we keep the same route, just shifting the traffic in a hitless way. So this has been demonstrated, and also in our lab. If you want, I have also a movie to show this. But what has not been investigated so far is if this is advantage enough, if we have to keep the route the same, or it's better to apply some more traditional defragmentation or re-optimization solution where we switch off the traffic. We have maybe an IP layer with 2 routers and each one served by a dedicated optical connection, and we apply the make before break. So this is another aspect that will be considered in the project. And as anticipated, this solution will be investigated through simulations. In terms of control plane architectures, this control of the bandwidth variable transponder functionalities will be supported thanks to the use of an active stateful PCE architecture. So in this case, the PCE is not, say, the traditional PCE, the one that has been standardized so far by IETF, where it's just an element for path computation with no memory inside. But in this case, it is stateful, so it has it stores all the routes inside his architecture, his memory there, and is also active. So it can also decide at certain point to run a re-optimization in the network. So it has some, say, power there. And to consider this architecture, we also consider the fact that we will easily have to deal with a multi-domain scenario. For example, GÉANT is a typical multi-domain scenario which collects, which combines together different networks. So when we consider this kind of, say, new architecture, we also consider the presence of other premises with maybe different path computation element capabilities. And the fact that maybe we can also have a so-called back-end PCE, which has some specific functionalities in terms of algorithm and in terms of solution. And we also have to deal with the problem of how to provide traffic engineering information to these nodes. And to this extent, we will rely and we will investigate this BGP-LS solution. BGP-LS is a new protocol. Basically, it relies on the BGP protocol, but there's nothing to do with, say, the typical use of BGP. It will just be used to bring information, link state information inside a network, and to carry this link state information to another server, for example, another user, which could be a backend PCE. And so we will say the idea here is basically to investigate the most recent technologies in terms of path computation element architecture and control plane, say, GMPLS based. So all these control planes over here, this is the part of the BGP-LS. So one other, say, part that is going, that the IETF is introducing is also the inventory database, because so what is often happen is that the element in charge of the online operation, so the traffic engineering operation is not the same element and of the one that does the planning. So the idea is to merge together, is to combine together these functionalities, and in order to provide more, say, effective resources. So we will also have to introduce what is called the inventory database. So we need to provide, trying to unify the path computation element using during traffic engineering operation with the one used for planning purposes. The third relevant aspect that will be addressed during the project is related to the algorithmic part. So in this case, UPC will be in charge of all the algorithms and strategies that will be applied in order to control the bandwidth variable transponder and the flexible grid optical network. and all the capabilities of the BVTs. And also considering the specific architecture of the control plane, so with the path computation element. And so there will be specific activities from UPC in order to provide, to efficiently support elastic operation, re-optimization, defragmentation solutions in an efficient way. So the use cases will be, say, as anticipated, the traditional use cases. So we will have to deal with provisioning, elastic operations. So when we change the rate of, for example, a certain traffic to serve additional requests, defragmentation, re-optimization, and also recovery mechanism. There will be also some experimental validation at the data plane level, and this will be done thanks to the collaboration with other projects. So here is some example of elasticity. So we have a certain connection that and more capacity is required to these connections. So we have to provide to this connection more spectrum resources, more capacity. If we just enlarge here, if we had just symmetrically some carriers, we will have a defragmented network. So we may need to shift the existing connection and then enlarge the connection. So this is just a little example of what we consider for elasticity. And this is another example just to give you an idea of the fact that the fact that we may have a path computation element in charge of a certain domain and another one in charge of the whole re-optimization may require some steps and synchronization events. So here the scenario is not so, say, simple, but everything can be handled efficiently, but we need to, say, work on this. Here is a sequence of operations. So when a certain request arrives, this path computation element can try to find a solution according to what is its capability, but if it is not able to find a route, for example, to serve a certain connection, it may request to the backend PC to run a re-optimization of the network. Re-optimization can be done by considering a sequence of operations, because it's important maybe the way re-optimization is performed. And so we need to introduce some synchronization among the various steps, so in terms of algorithm and related operations within the architecture. So this is another example of the solutions that will be investigated. This is another example for the restoration case. So we apply sliceability here, dividing the traffic when we move from a working path to a backup path. And here is just a slide showing the resources that are available in our labs. And so even if the project deals mainly with algorithm, control plane solutions and transponder architectures, we will try to achieve some demonstration. And in particular, this demonstration is some way connected with the Coffee project, in the sense that we will consider as a reference transponder for the transmission part the transponder used by the Coffee project. So there is a connection in some way. So if you have questions or curiosity so far.
The use case of BVT, is it a network-to-network interfaces or this client and the user to
interface? Are you talking about the data plane transmission or the data plane transmission? Okay. So here the idea is that each of these photonic integrated circuit has to be provided with some tributaries. These tributaries come from tributary cards, so from routers, for example.
Kind of digital cross-connect.
Exactly. Here we may need a digital cross-connect if we want to provide adaptation from one modulation format to another. But maybe we don't need to go at the level of a packet because, for example, we may have tributaries at 25 G coming from dedicated ports or OTN framing, for example. So, according to the requirements here, we may consider different solutions. Also, combination of switches 1 by 2. Either electronic or with, again, photonic integrated circuit there. So,
the first question regarding the sliceable DVT. As I understood, the only goal to have the sliceable DVT is to be able to just grow from a certain channel capacity to higher channel capacity. But you lose some spectrum. But also, you in the first case, to the left, you have several lasers, or you have several ports, link ports, don't you?
Yes. For example, here, in this case, we have 5 different carriers. Okay. In order to save cost, so the difference between a simple combination of WDM cards with respect to this solution is the massive use of photonic integration, photonic integrated circuits, and the sharing of resources. For example, here we rely on a single multi-wavelength laser, which is a simple circuit which relies just on one laser used by all these carriers. And here they are depicted separately, but actually this is expected to be a single chip. So in principle this can be assumed as a combination of WDM cards, but in practice the idea is to exploit the integration here, and so to save also energy and to have some benefits. But then here, when we generate different carriers, if we keep them on the same route, we can keep them very close, very packed one each other. On the other hand, if we route each of these carrier in a separate way, we need to account for filtering effects in transit nodes, for example. And filters are not ideal, so we have to separate them, and so we also have to deal with the granularity of the flex grid, which is at the moment 12.5 gigahertz. So we have to consider these kind of steps, and so there is some drawback when we separate them. We also need to have a multi-wavelength source that needs to be configured in order to be able to shift. There might be another drawback that this flexibility may also impose that we cannot assign each wavelength independently. Maybe we can tune the whole comb, but once the central frequency of the comb is fixed, then we must use this frequency, this frequency, this frequency, and it's difficult to find along different routes exactly this amount of spectrum around this frequency free toward a single destination. So sliceability is also related to the way the technology implements these functionality. So these are just some examples.
Not only, but do you see any future for the sliceable stability?
I think it's in principle, even if we enlarge here the overall spectrum, this can provide some benefit because it's something that is an additional functionalities. We can always rely on that, but if needed, we can also apply this scenario. So it's something that is added. And from a technology point of view, it comes for free because we just need to have a configurable multi-wavelength source. In with the schemes that we are considering to generate this comb is not a problem to tune the wavelength. So this actually comes for free. But at the moment, we are not able to assign to each of these carrier any wavelength. So we have to keep them separated. We have to keep them closed one each other. So I have to say that it's something that comes for free. So it may provide some benefit.
For the control plane, you are only going to simulate it?
No, there are experiments are the simulative part will evaluate these BVT solutions and performance. But in terms of experiments, we will exactly implement this architecture. So there will be 3 different path computation elements, one in the CNIT premises, one in the UPC premises, and one in the Telefonica premises. So, for example, our PCE will be active and stateful and will control the FlexiGrid optical network. Here in which is partially real and partially emulated. We have only few nodes, real nodes, so we can enlarge that with with emulation. In Telefonica, they have as well some Cisco FlexGrid nodes commercially available, as well as an emulated network, and these will be controlled by a stateless PC that they have implemented. And also in UPC, we will have the backend PC with advanced algorithms, say not simple heuristics or simple solution as we have in these 2 domains, but also here there will be a PC, and so everything will be real. Yeah. For example, in our case, we can we just rely on our 3-4 nodes, depending on the kind of experiment, and we will add some. Basically, we have these 3 nodes with the data plane inside, plus some little PC Linux boxes. Where GMPLS control plane runs, and in particular we have RSVP extended for FlexGrid, but for these other nodes there's no cross connect behind, so it's just a Linux box without the data plane behind. Is
Dragon-based?
No, it was implemented. It was implemented in our lab in these years. It's a lightweight RSVP. It's not a fully operate, but it's basically it includes all the functionalities required for FlexGrid, but maybe some other functionalities are not included, like some. And while, for example, here in Telefonica. They have the emulation comes from I think some open source facility, but I'm not sure about that. I can ask.
In the OpNet simulations, what exactly are you going to? Because you say that it's going to be related to the transponder itself.
Yeah, for example, this sliceable functionality is something that we are investigating. For example. If there is a failure, we have a super channel. We can evaluate if it is possible to recover all the destroyed connection by maintaining a super channel packed together, or if it is beneficial to also apply sliceability, since we occupy more spectrum resources, even if along different routes. So this is a typical simulations that will be.
No, but it's not going to implement any kind of actual physical layer definition of a recovery scheme, for example?
For example, the spectrum resources that will be configured in the simulator will be exactly those that are validated in our lab from a data plane perspective, and also the optical reach is the one that we are able to guarantee with our real transponder. So we will consider the parameters that come from our transponder, real transponder.
Do you know the cost you get when you have to introduce BVT? So you have to, so it comes as an extra cost, so you have cost a lot of, you know, the factor of how more expensive actually a BVT is compared to the fixed transceivers. Is it a factor of 2, 3, 4, 5?
We are strongly investigating photonic integration. So if we are able to run all these transponder with a single chip, that is the target that we are doing, not in this project, but in general in our lab, this part will be not expensive. What is expensive then is the fact that we run to achieve 1 terabit. We have to operate at the electronic speed for the FAC, for example, for the decoding, and the electronics is the top speed, so this is expensive. But the optical part is going to be cheap. This is the target.
A few words about coffee?
Yes, sure. About coffee, I can show you this slide. In the coffee project, they will target the transmission part only, in the sense that they will try to pack together as much as possible to increase as much as possible the spectral efficiency. So given a certain baud rate, the maximum available baud rate that the electronic is able to provide, so 1 terabit transmission will be achieved thanks to the use of multiple carriers, as in our project. And their target is to pack these carriers as much as possible in order to increase the spectral efficiency. They have studied a different technique. Let's say so far, most of the studies in terms of high capacity and high rate transmission considered either OFDM or Nyquist WDM as transmission techniques. OFDM was mainly used at the beginning. Nowadays, people tend to consider to do not consider OFDM anymore, at least for the long haul transmission for the transport networks. But most of the studies refer to Nyquist WDM, and when they want to be very efficient in terms of spectrum resources, they consider 16 QAM transmission, which, however, has some limited optical reach. The solutions that in these years my colleagues have studied is a different technique. They call it time frequency packing technique, and the idea is that thanks to the use of coding that is derived from the radio world, so LDPC coding, they are able to strongly overlap the carriers, introducing inter-symbol interference and also inter-carrier interference. So they are really overlapped. They do not rely on 16 QAM. They will use DPQPSK, but with a strong overlap in time and frequency. But thanks to the use of this coding technique, they are able to understand the inter-symbol interference and the inter-carrier interference. And so they are able to detect this channel. And so the expected performance are even better using QPSK than those provided by 16 QAM in terms of spectral efficiency. These are the results published and experimentally validated from, I don't know, Nyquist WDM, Cisco, and several other points. And as you can see, they suffer from two main drawbacks. One is that they are a little bit less efficient, and the other one is that they have steps that are quite so they are not easily tunable according to the optical reach, in this case the OSNR. While this technique enables to adjust the coding with introducing a little bit of overhead in a very configurable way. So according to the path, we can always try to maximize the spectral efficiency. And in general, this technique is more efficient. These dots are achieved through simulations. So what they are going to do in field trial is to validate these dots. I have to say that they have already done several experimental validations. For example, they had a field trial in Australia from Melbourne to Sydney from Telstra. And so is something that has been studied in these years. There have been some preliminary simulation, experimental validation. In that case, there was a fixed grid in the middle. So they had the constraint in terms of notches provided by filters and WSSs. Here they are moving forward with the technique for the packing the carriers, and also they will say do not consider anymore these constraints.
I see that many of these field trials which is done with achieved by spectral efficiency is done on a new fiber with a very large effective area, and
no. These
also maybe many of them they're using very shorter amplifier span. Is it considered like something like that? So
yeah.
the fiber amplifier spacing.
The coffee project will run this test on the existing fiber infrastructure provided by Geant. I think the link is the one from Milan toward, don't remember the name, in Germany or Austria. Vienna. Vienna, yeah, okay. And so this will use the installed fiber, and in terms of amplifiers, there are Alcatel amplifiers already installed, so they will use exactly this infrastructure, just inserting the transponders in Milan and Wien, and so we will see their actual performance. But I agree with you that when you see the experiment, there's always a short reach. For example, I can show you an OFC paper that we have published using this technique in OFC 2003 and 2013. And in this case, with different coding, we were able to reach 5,000 kilometers. But here the span was 40 kilometers among amplifiers. However, we expect that, of course, it will decrease when we consider, say, 80 kilometers or 70 or 80 kilometers among amplifiers. But in any way, we expect a good performance.
So, as an NRAN or operator, actually, what we consider as what is a big consideration for us, actually, when we are building a new DWDM system and start building from scratch. So that's the question is, should we go for shorter amplifier span, or we have to keep this 80 kilometers or 100 kilometers? And a question like this should be very nice to address also, actually. What kind of fiber should we use? Should be
in terms of
effective area, because this you have many different fibers available in the market, but the price differences is also huge, actually.
Yeah.
So if you buy the most expensive fiber but get nothing in terms of capacity, so you actually waste of money. And also if you have shorter amplifier span, you also have considered that you have more amplifiers sites and the cost of housing, operational cost will go up. So you have get something back.
Yeah, according to, say, our experience, this kind of transmission is very robust. So coherent detection strategies with this kind of modulation format and coding is very robust. So I think that this enables the savings from an infrastructure perspective. So we can keep the same 80 kilometers, typical distances, 70, 80 kilometers. We can keep the same optical fibers, because they are this kind of transmission, it seems, according to the results so far, is very robust.
So even if you consider about 10, 15 years perspective, because when you build an infrastructure, actually, then you think that it will, stay for some years. When we are going to 1 terabit per second per channel, and larger distances, so the current fiber structure with current amplifier spacing is it sufficient? It's good enough.
In my opinion, yes, this is enough. Also because 1 terabit transmission will probably stay in just 150 gigahertz. So there's and covering large distances with these typical span kilometers. So I think that for several years there is enough capacity on the existing fiber technology and fiber infrastructure. But we can investigate this aspect. It's a good point. If you are interested, we will be happy to investigate it.
We are doing build new systems, and then the question is what kind of fiber?
Yeah.
What kind of size?
Yeah. Also, if you think about the G653, when it came, everyone started. For example, in Italy, Telecom Italia started to install this kind of new fiber because they expected to be more, to provide better performance. But then WDM came, and this kind of fiber was not so suitable for WDM. So I think that of course, it's difficult to foresee the future, but I think that the current, this transmission technology is robust. Yeah, anyway, if you need additional questions about this technique, Luca Poti is the coordinator of the project and can provide you additional information better than me.
Thanks for that.
Thank you.
Continue with the internal task meetings.